So now I want to show you another method that we can apply with our currently available techniques before we get into all the linear algebra stuff. And again, this is one of these things that I'm showing you that's not actually so important. We're not going to keep using this method, but it's useful because it's already available to us. So it gives us a way to sometimes get to an answer with the methods that we already know. And this gives us a chance to look at what kinds of answers look like, what the answers can look like before diving into all the linear algebra. So it's useful to just use this as a way of getting to an answer quickly and then becoming familiar with what answers look like. Okay, so here's the example that I'm using, and what I'm going to do is called the method of dividing. So these are two unknown functions of time, right? So this is, you could write it like this, right? It's basically just this. If you think of x with the vector symbol as packaging together x of t and y of t. So this is definitely one of our kinds of systems that we're interested in this chapter. It's a constant coefficients, linear, homogeneous system of differential equations. And you've got two unknown functions, x and y. Now, the method of dividing says, basically, it suggests that you do this. Look at y prime over x prime, or x prime over y prime. I'm going to choose y prime over x prime. That's dy dt over dx dt. And if you pretend that this makes sense, then that's like dy dx. Okay, what's really happening? What's happening rather than the cancellation here? Probably what's actually happening is we've got dy dx times dx dt. And according to the chain rule, that's the same as dy dt. As long as there's a way to express y as a function of t via y as a function of x, right? As long as there's a way to get y as a function of x, as long as it makes sense to get y as a function of x. Of course, it does not always make sense to get y as a function of x, but for those regions in the solution where it does make sense. So let me give you an example of what I mean. If your y of t and x of t are traveling along a circle or something, along this portion where it's the tangent is vertical, near this region, it does not make sense to say y is a function of x, right? Because it fails the vertical line test. Any given x value gets associated with two possible y values. So this doesn't always make sense, but in most places along the circle it does make sense, and that's going to end up giving us useful information. So if you can express y as a function of x, then y of x of t is y of t. And so the chain rule tells us that we can do this, and one notationally convenient way to think about the chain rule is that it's as though these are canceling, right? So it's the same kind of idea here. It's as though these t's are canceling. All right, so now divide this equation by this equation, we get on the left side y prime over x prime, which we have just decided is dy dx, and on the right side I get negative 4x over y. Now what would you say about this differential equation? This is now in the unknown function y of x. T has been eliminated completely from the picture. So it's now a differential equation with one unknown function and with x being treated as the independent variable. So it's kind of weird, right? Like here we started with everything being a function of t. T was the independent variable, and x and y both depended on t. But now we've flipped things around. X is the independent variable, and we only care about y's dependence on x. So we're down in this funky way. We got ourselves down to one unknown function of one variable. Okay, well this is separable, right? Just do this. And there, it's separated. Now, integrate. And let's see, let me try to solve for y as a function of x. So I get y squared is negative 4x squared plus, let me call it c2, or d, how about? And so y is going to be plus or minus, depending on what branch you want to pick, that. So that's kind of interesting. So that what that tells us is not how y and x depend on time, but it tells us how y and x are related. So it's telling us the shape of the trajectories in the phase plane, but it's not telling us exactly how those trajectories are traversed. Now, if you want to know what shape this is, I would actually probably not solve, and I would just stick with this. If you stick with this, maybe write it like this. Let me do the x first. I don't know why. 2x squared plus 1/2 y squared equals constant. What does this look like? Well, what if these constants in front were 1? Then what would it look like? This would be a circle of radius square root c, right? But with these constants, what happens? It kind of stretches and morphs it, so it can become an ellipse. So this is an ellipse. Maybe a nicer way to write it is like this. Possibly a nicer way to write it. So anyway, you've got this unknown c here, right? So what's the deal with that? Well, we shouldn't be too surprised, since differential equations depend on initial conditions, right? So here, to have initial conditions, you would need to know sort of what is x of 0 and what is y of 0. Or it doesn't have to be time 0, it could be any given time, but let's just say 0. So this would be what an initial condition is at the very beginning. So for every, so let me put it this way, if I draw the phase plane here, x, y, given any initial condition, there's a trajectory going through, right? And it doesn't have to loop back on itself, but yeah, for any initial condition, there's some trajectory, right? But you need to know where the dot starts so that you can then decide where it's going to go. So what's going on down here is we have found the shapes of the solution trajectories, and for different values of c, you can get different ellipses. So maybe I'll go to Mathematica to plot this. So if I, so I could just plot this function, y equals square root of this, or I could plot this equation. So it is possible to give Mathematica kind of an equation relating x and y, and then ask it to just plot the curve that satisfies that equation. So it's called a contour plot, if I can spell that. And let's see, I think this will work. Then let's do equals, let's start with equals 2, and then I'll change this constant 2 to something that maybe I can manipulate, or maybe I'll just show a bunch of values. And then I need to give 2 ranges, one for x and one for y. So I don't know. If it comes out not big enough, I'll figure out how big it needs to be. And missed the comma there. There we go. So it's an ellipse. And then if I choose different values here, it'll for the c, it's going to change the size of the ellipse. So these are accounting for different possible initial conditions. If you start somewhere else, you'll travel along a different ellipse. Let's see. So maybe I can put a little lowercase c here, and then do a table, so this way it generates a list for different values of c. So let's do c equals 1 to c equals 5. And then instead of showing me them listed like that, show them all on the same plot. Oh, cool. I bet I can fit more of them in there. How about 20? Cool. So you see, for different values of c, that's neat. If I hover over it, it tells me the equation for that curve. So for different values of c, I get these different trajectories. So of course, I'm only showing like integer values of c, which there's no reason to do that. I could separate them by finer increments. Basically, every point in the face plane, this is the face plane, right? Horizontal x, vertical y. For every point in the face plane, for every choice of initial condition, that point is going to be sitting on one of these ellipses, and then what it will do when you play it out is it'll travel along the ellipse. Now, how will it travel along the ellipse? Will it go clockwise or counterclockwise? Will it travel quickly or slowly? Will it travel at different speeds along different portions of the ellipse? All of these questions are totally not answered by this x-y relationship. If you want to answer those questions, you need to know what is x of t and what is y of t. Now, you do have a way of doing that by the method of elimination, the thing we saw in the previous video, but one of our goals is not to have to do that, and instead to stick with writing things kind of in this form and come up with a good way to describe the trajectories, and use linear algebra to understand what they're doing.